This Ampere circuital law is actually alternative to Biot law. And as you know, we have learned Biot law in the last two classes. And Biot law helps us to calculate magnetic field for any symmetry, whether it is straight wave or it is infinite or finite or whatever. But Ampere circuital law is applicable for highly symmetric objects. When you see there is a high symmetry, then you can apply Ampere circuital law. So in the Ampere circuital law, what you need is actually what is considered is an open surface with a closed loop. I think you people are able to see like a balloon, okay, or maybe a sack. A sack, if you have, see the mouth has a boundary of a sack, and this is the open surface. This is the surface, open surface, okay. And you look, this is the mouth of the, or maybe you can just consider any pot kind of things like that, okay. Any pot. We'll see this kind of various kind of surface again in our 8th chapter when we will be discussing electromagnetic wave. Okay. So in this Ampere circuital law, we need to have an open surface. This is an open surface. Open surface. And you look, there is a boundary to it. So this is boundary. Okay, this is a boundary. Again, this is another boundary. So it has a boundary. Open surface, but it has a boundary. So we'll be considering such kind of things in this Ampere circuital law. In fact, I'll just show you another. So this is from your book. Look, this is kind of this one, and it has, this is the surface, open surface, and this is the boundary to it. Okay, some kind of pot, right? So this is, say, this is the surface and this is the boundary. Okay, and see, to apply Ampere circuital law, the current has to pass through both the boundary. So this is the open boundary. This is open boundary. At the mouth of the, see, as I showed you, if you consider a kind of a pot, you have this mouth. Okay, this is the mouth. This is the boundary of the surface. Even this is also boundary of the surface. Okay, so in this case, let us see the closed boundary. There may be many closed boundary, but the closed boundary has to, this is a closed boundary for this case. This is a kind of a circle for this surface, open surface. So if the current is actually passing perpendicular to this closed boundary, like this, it is passing perpendicular, and it is passing through the surface, okay, then we can apply Ampere circuital law. You can apply Ampere circuital law. And you look, this closed boundary is called actually Amperian loop. Okay, this is called Amperian loop. The closed boundary, if I take the boundary in this way, like this, so I have just cut this boundary and then drawn here, suppose. And so this is the Amperian, this is called, this loop, which is one of the boundary of this surface, open surface, is called Amperian loop. Amperian loop. And look, this Amperian loop is perpendicular to the current. So this, if this is a wire which is passing through this open loop, closed loop, it is passing through it, and the current direction is perpendicular to the plane of this loop. Perpendicular direction of the current is perpendicular to the plane of this loop. Okay, so when we are going to write the Ampere circuital law. Statement is actually, so let us see what we can write. The statement is B dot dl, okay, B dot dl is equal to mu naught into I enclosed. Okay, I'll explain what are these terms. So this is an integration, and this sign says that closed line integral. This is a closed line integral, integration is closed line integration. Okay, closed line integration. And what is that line? You look here, this Amperian loop is actually kind of a circle. It is not a surface, it is kind of a circle. That means it has periphery. So it will, if I want to calculate the periphery of this circle, a perimeter of this circle, it will be some kind of 2 pi r. This is the total length. This is the total length of the loop, Amperian loop. Now look, I have to calculate. Suppose I have an infinite wire. Okay, suppose I have an infinite wire. Okay, straight wire. So here I have what? I have cylindrical symmetry. If you remember, I had discussed in case of electrostatics, this law is kind of a Gauss law, So in electrostatics, we have discussed that when we have a straight infinite wire, we have to think of cylindrical symmetry. What does the symmetry say? Symmetry says that the electric field, in that case, electric field will be always radial. Okay, radial, and over the surface, if I just draw this circle, so at each point of this circle, it is a constant quantity. It has constant value. Okay, for this. Okay, so and the magnetic field will flux will be only through the curved surface. So that was the symmetry in that case. So in this case also, when we talk about a straight line, we can talk about cylindrical symmetry. And according to cylindrical symmetry, you know, the magnetic field will be actually see at distance r. If I just take this whole loop, it will create a magnetic field which is constant, having a constant value over this loop, constant value. That means magnetic field will be having constant value. If I take this point or this point or this point over this circular loop, the magnetic field, the magnitude of the magnetic field will be constant. So that is one consideration. And another important point is, so this type of integration is called tangential integration. So here in this case, you know, the magnetic field you have to take is the tangential component of the magnetic field. Tangential component of the magnetic field. Okay, so tangential component of the magnetic field means the direction of the magnetic field has to be tangent to the point I consider. So if I say at this point the magnetic field direction will be okay, so this will be like that. Okay, so it will be tangent to that point, particular point. So first of all, magnetic field will be constant to every point. Okay, and it will be tangent. You have to take the tangential component of the magnetic field, and there by symmetry, in this case, magnetic field will not have any normal component. It will have no normal component. You will have only tangential component. Okay, this will be non-zero and a constant value. Now look, if I have to calculate magnetic field for this whole wire, what I have to do, first of all, I have to consider, see, if I want to calculate magnetic field at this point P, so I have to consider it. I have to draw an Amperian loop of radius R. So this is not true for all symmetry. This loop can be of rectangular symmetry. Okay, any symmetry it can have. Okay, depending on the problem given. So in this case, the straight line, so it is cylindrical symmetry. So I can take the imperial loop as a circle of radius r, suppose in this case, because this P point is at r distance away from the wire. And the current flowing through the wire is actually I. So if I consider a small length of this loop, as you can see from here, one loop is one small length element is shown here, this one. And look, the direction of this, so this is dl, so this is having a length dl, a small length element of this loop. And see, it is a vector quantity, but what is the direction? The direction of this length will be actually along the tangent of this circle or particular part. If you take at this point, this is dl, suppose, but the direction will be tangent to this. Okay, if you take another loop, another small element here, the direction of this element will be like this. Okay, so towards tangent. So you can see that B and this dl, these are parallel to each other. Otherwise, this is a dot product. This integration is a dot product. So you will not get any value if B and dl are perpendicular to each other. So look, so this part, I hope you have understood now. That, see, I have to consider a small element of the loop I have considered, and I need to see at that particular, I need to see the direction of the magnetic field at that particular element of the loop. So these two are, look, these two are, since it is a circle, these two are parallel to each other, because I am taking magnetic field as tangential component. Sometimes it is written as BT. So tangential component of magnetic field, and the dl, the length element of this circular loop, is also along the tangent to this particular part of the circle. So that's why these two are parallel to each other, and I have to take closed loop integral. That means if you take small, so many small length element and then add them up or sum them up, then you get this integration. If you take very small value of this dl, the summation will get converted to integration. So that's why it is written integration. I think Samhita, can you just mute yourself? Okay. If you have any question after I finish, kindly ask question after I finish. Okay. I'll give you some time. Okay. So this part, I hope you have understood. This left hand side part. So since B is constant, okay. So B is constant in this case. So what you can do is actually, and this B, we have seen that the magnetic field and the component of this length element, they are parallel to each other. So I can just make this as a scalar quantity with a closed integral like this. And mu naught is actually permeability in the free space, and this is the current which is passing through. Okay, which is passing through this loop, That's why I can write as enclosed. Okay, enclosed by this loop, Amperian loop. Okay, so in this case, small I is the current enclosed by this whole Amperian loop. So since this is a constant quantity over the loop, so I'll just take that out of integration. So only integration I have to do over the loop. And look, this is mu 0 I, because I is the current passing through this loop. So what I get is actually, see, if I take the integration of this dl, that means if you take small and like for the whole, so this integration of this length element will give you nothing but this perimeter of the loop, circular loop. So what you get actually is what you will get actually is this B into 2 pi r. This is the perimeter. I have got this upon integrating this dl over the whole loop. So this is 2 pi r. That is nothing but perimeter of the this Amperian loop, and this is equal to mu naught I. I is the current which is passing through the loop, circular loop. So this will be actually the expression, and loop final expression I can write this as mu naught I by 2 pi r. So this is the magnetic field at r distance away from a straight infinite wire which is carrying current I. So what I get is this one, mu naught I divided by 2 pi r. 2 pi r. So r is the radius of the Amperian loop, okay, and I is the current enclosed by the Amperian loop or passing through the Amperian loop. So this is how you can calculate the magnetic field, okay, as an alternative. So this law is an alternative law for Biot-Savart law, alternative to Biot-Savart law. But in this case, you have to be very much careful while applying this law. You have to first consider the Amperian loop properly according to the symmetry. In this case, I have taken cylindrical symmetry. That's why the Amperian loop is circular. But in some cases, you will see the application of this Amperian circular law is there in case of solenoid and toroid, which will be doing that. Today, I think I'll just I'll try to take at least the first of that, the solenoid. So what you can see from here, magnetic field is directly proportional to the current passing through the Amperian loop, and it is inversely proportional to the distance you go away from the wire. So according to this, like if you increase the current in the wire, you get more magnetic field, and if you come closer and closer to the wire, the magnetic field actually will blow up. So it's tending to infinity. Okay, if you come closer and closer, when R is tending to 0, the magnetic field will tend to blow up. Okay, so there are certain limits also in this case for Ampere circuital law. You cannot use very close point or at the center if you want to calculate magnetic field. Okay, you may not be able to calculate because of this. Okay, so any current carrying loop like this, we have learned already from Biot-Savart law. We can calculate magnetic field at the center. Okay, all right. So this is Ampere circuital law. So the statement was that the closed line integral of magnetic field, okay, B dot dl, okay, tangential component of the magnetic field, closed line integral of the tangential component of the magnetic field. So what is that? Closed line integral of, okay, I'll clean everything first. So the statement you can write is actually closed line integral of the tangential component of magnetic field. I'm writing B simply. Magnetic field you have to write. Closed line integral. So is equal to mu naught times the current passing through the Amperian loop. So you can write a Amperian loop. Okay, or even you can write open circuit. Open circuit. So this is the statement, and the mathematical form of that statement is this: B dot dl. You have to obviously draw this, and then write this B dot dl is equal to mu naught I enclosed. Okay, so this is the way you have to write Ampere circuital law. So there will be a common question for all of you in the board exam. They will definitely ask what is Ampere circuital law and how to calculate the magnetic field or calculate the magnetic field for an infinite wire at a distance r. Okay, so that is what I have just explained so far. So now we'll see few characteristics of this Ampere circuital law, which are written in a book. I have already told some of them, but still see here you have to take the tangential component of the magnetic field, which is non-zero and constant. There is no normal component. Okay, so B vanishes, and this is okay. So I have already told almost few more. So it implies that the field at every point on the circle of radius r is same in the magnitude. In other words, the magnetic field passes through possesses what is called cylindrical symmetry. This also I have told. So I think I told all the points. So you people should read the text and see if you have any doubt, any questions. Now itself you can ask, or maybe after reading this part, if you don't understand anything, you can ask me again. Only one more thing I have to tell here, about the direction of the magnetic field. So I'll just tell you what is the direction of the magnetic field here. So suppose I have a straight wire like this, and it is carrying current I. So as you know, magnetic field will be mu naught I by 2 pi r. If the distance you are interested to calculate magnetic field at this point P, which is at r distance away from the wire. So now you have to tell me what is the direction of the magnetic field in this case. I have told you, like, so you can write, you see, right and thumb rule you can use, right? So if you just keep your thumb, okay, thumb along the direction of the magnetic field, sorry, and the current direction, like, okay, so I think I have already shown you this. So this way, if it is pointing, and if you just want to grip the wire, okay, grip the wire, then you'll see the direction of the tip of your fingers, or other 4 fingers. If you just keep your thumb finger along the direction of the current, thumb finger along this direction, thumb finger of your right hand, and you try to grip this wire, okay, in this way, then you look, your tip of the finger will go into the into the plane of the paper. So magnetic field will be here into the plane of the paper. But what about this point? This point, at this point, your fingers will come out of the plane of the paper. So here the magnetic field direction will be out of the plane. Okay. So consequently, you look the magnetic field lines. If it is if the current is flowing like this, so you'll get at r distance magnetic field in this way. Okay, in this way. If you apply your right hand thumb rule properly, okay, and if you, so this, suppose this is r1 distance, if you go r2 distance, again r2 distance, so then you will get another circle like this. So this is how magnetic field lines will be, actually magnetic field lines will be kind of concentric circles. Okay, you'll see concentric circle around the wire. Okay, concentric circles like this. Okay, and the direction will be given by the right-hand thumb rule. So this is how you can find out the direction of the magnetic field. Okay, so I hope you have understood this. Then I'll go to the application part of this. Let us go to the application part of this. Like one application you can do. So this is from your book itself, NCERT textbook, the example number 4.8. So we'll apply this Ampere circuital law so that we understand properly. And yeah, so you see this figure shows a long straight wire of circular cross section whose radius is A and carrying a steady current I. Steady current I. The current direction is given this way. Okay. The current is uniformly distributed across the cross section of the wire. Current is uniformly distributed across the cross section of the wire. Okay. Calculate the magnetic field in the region R less than A and R greater than A. That means what? R less than A. So A is the radius of the wire. Okay. Radius of the wire. So R less than A, that means interior of the wire, interior point, at any interior point. Okay. At any interior point. And R greater than A means any exterior point. Okay. So R greater than A. This is A. So exterior point, you can take Ampere loop like this. Okay. So here already the figure is drawn. I'm not going to draw again. So look here. You have to apply this Ampere circuital law. What you know Ampere circuital law? So this is also straight wire, straight and long wire. So I can take the cylindrical symmetry. Then I can write this B dot dl. Let us so always what you do, you just write the main law you know. Enclosed, I am writing En, suppose. So here we have to first draw the Ampere circuital Ampere loop. So I'm just going to calculate first for R greater than A. Okay, R greater than A. So greater than A means any outer point. So this is suppose point P, and here the Ampere loop is this one circular, and this radius of this loop is R. So look here, we have discussed that by the cylindrical symmetry, the B is always tangential. Okay, always tangential. So I can just take that out, and since B and DL they are parallel to each other, so dot product will give you a B DL cos 0. That means cos 0 means 1. So B DL, you'd have got B DL. So B is constant over the loop. So I just take out of the integration. So I have to just take the integration of this now. And so what is the current? Current passing through this Ampere loop. So this loop looks like parallel to the wire itself. It is not. Actually, the loop is actually perpendicular to the wire of the or direction of the current. Okay, direction of the current. So that's why it is passing through. And you know, when I consider the Ampere loop having a radius greater than A, having a radius greater than A, then the whole current is actually enclosed by this loop. So I can write this as I. Okay. So this side again, I can write B into 2 pi R. This is very simple. And this side is mu naught to I. And so this implies actually mu naught I divided by 2 pi I. Very nice. So B is actually proportional to 1 by R. Okay. So this you have understood now. Okay. So I have got, so I'll just write it. The result I'll write. The first result is B at r greater than a, which is mu naught I by 2 pi r. Okay, now I am going to calculate the second part of it. So magnetic field I have to calculate at r less than a. That means any interior point. Look, I am just drawing here for your set. So suppose this is the center and this is your A. So I have to take any smaller shorter radius of it. So I am just taking this as R. Okay. Then I have to draw an Ampere loop, and same thing like here also will be circular loop. Suppose this is the circular loop of radius smaller, but it is an interior point now. So in this case also the same loop will be like this. DN will be like this. Okay. Only thing there is that what is the current enclosed? Is the whole current passing through this Ampere loop, or some of the current is not passing through it? Suppose the current is passing current direction in this way. Look, see, some of the charges, see, it is current means flow of charge. So some of the charges will go pass through this gap, right? This gap also. That means all the charges are not passing through this particular Ampere loop. So I cannot write I enclose as I cannot write this. This is not the enclosed current by this Ampere loop in this gap. Okay. So I have to calculate what is the current passing through this particular Ampere loop when I am taking an interior point. Similar to a solid sphere, solid conducting sphere, okay, sorry, not conducting sphere, which we have discussed already in the electrostatic case when we were applying Gauss's law. That time inside there are charges. So enclosed charge was not exactly the charge when we were calculating the electric field outside, right? In this case also, the current is not the whole current which is passing through this particular Ampere loop now. Okay, we calculate that. So before that, I'll just at least complete this thing. So this will be D. Again, this will be 2 pi r. So I'm just writing here. This I enclose I have to calculate. I'm writing here 2 pi r. Very nice. 2 pi r. So this is all. Okay. Now what we have to do? We have to find out I enclose. So see, it was the current was uniformly distributed over the cross section. That means what? I can find out the current. So this is the total current passing through the area pi r square. So I can find out the current density. Okay, current density or the current passing through unit area. Since it is so, the I enclosed will be current passing through unit area into the area of the Ampere loop, which is pi r square. Okay. Now pi goes up. Okay, so I just write it here directly. So what we have got here now then, see, this is mu naught I into r square divided by a square. Okay, so 1 r will go off with this, and then what you get is this now, b mu naught I by mu naught I into r by 2 pi a square. So look here, now I write the result here. B is actually mu naught I into r divided by 2 pi a square. Okay. So this is what we have got now. So look, in case of exterior point, the magnetic field due to this infinite wire is actually varying inversely with the distance from the wire. But when you consider an interior point, the magnetic field is actually varying as directly proportional to, so interior point B is directly proportional to R, and B is varying as inversely proportional to R when you calculate the magnetic field for this wire exterior point. So this is interior, and this is exterior point. Okay, so this is how you have to always keep in mind that B dot dl is equal to mu naught I, that I enclosed, you have to always take consciously the value of the I enclosed. Since we have considered the interior point over here, that's why I have to take different current than I. And when I have taken the Ampere loop outside the wire, the whole current was enclosed by this loop itself. Okay, and the whole current was passing through the loop. So now look, if I draw these two, okay, if I draw these two, uh, if you have been asked to draw the magnetic field due to this wire, okay, so how does that vary? Look here. Suppose this is the center of the wire, this one, okay. So and this is the A, and I have a distance R over here. So this is actually the distance from the center of the wire. So till the radius of the wire, it varies directly proportional to R, and then exterior it is inversely proportional to R, so it will be like this. Okay, it will be like this. So B is inversely proportional to R. It will falling off, okay, exponentially. So this is how you have to draw the magnetic field for this wire. It is already solved in your book. You can read again and then try to understand. So the similar kind of graph you would have seen in case of electric field also for a solid non-conducting sphere. For a solid non-conducting sphere also, electric field vary like this up to center. This is proportional to R, and then outside this it will be like this. Okay, so electric field is inversely proportional to R square. Actually, it is R square, not R square. Okay, electric field falls off as R square, 1 by R square. Okay, so yeah, so we have now learned this also. So now what we'll do, we'll just see the application of Ampere's circuital law in our practical life. There are various applications in our practical life. Among them, two are the most important equipments. Those are very much used in our modern technology. One is actually solenoid, and the other one is toroid. So today we will try to discuss this. Okay, we have got another, I think, 10-20 minutes because we have started at 16. I'll go up to maybe 17 or 7, 20 or 15. Sorry, not 50, 20, 7, 15 maximum I'll go. So please be patient and hear this. This is an important. So today we will discuss a solenoid. So that is very important, like part of our life. In the television, in the radio, everywhere actually it is applied. And in case of say synchrotron or many places, this solenoid is used. Actually, we have solenoids in even fans and etc. Okay, let us look in the power stations also there are solenoids etc. So let us see what is a solenoid. Solenoid actually is simply a windings of wire. If you take a long wire and then make some loops, okay, or windings, okay, windings, but that windings has to be in the same direction. Look here, it started from here, then it is going like this, then the next one going like this, like this. So the windings has to be actually in the same direction, okay, like this. And look, generally copper wire is been taken, and this wire is actually insulated wire. That means outer. So if they touch each other, they will not be making short circuit. They will not make short circuit to each other. So insulating. So these are called insulated copper wire. So insulated to each other actually insulated. So this is this is called a loop. Okay. So in this case, this is one loop, then another loop. This one. This is another loop like that, and each loop will create a magnetic field. As you can see in the Circuital law, we had seen when a current carrying loop is taken, then it creates a magnetic field along the direction of the axis. So we had calculated the magnetic field, and at the center also there will be magnetic field, okay, for this loop. So see, why do we use solenoid instead of a single loop? Because single loop creates some magnetic field B1. If I take some n number of loops, so you can get a stronger magnetic field, okay, stronger magnetic field. And magnetic field it creates actually, if I take this solenoid as long solenoid means length, if this is the length and radius is r. So length, when the length is much greater than the r, then it is called long solenoid. This is called long or infinite solenoid. Okay, it can be taken as infinite solenoid. So see, sometimes in physics, symmetry and this length, like finite, infinite, long, short, these are some advantageous points which always physicists are seeking for to solve any problem. Okay, whenever there is symmetry, we can easily find out physical parameters out of that. Okay, so you can understand why do we need a solenoid, because to create a strong magnetic field, a large magnetic field. And why only solenoid? That can be answered. Okay, so this is suppose a practical. If you go to the lab, you'll see this is a solenoid. So there are actually many wires. Okay, so look, the previous one. This is simply a wire which has been bent in the form of lobes, many lobes. But in this case, in general, whenever you go to the lab or in our application purpose, generally there will be an insulating material, kind of cylinder, and on top of that, the wire, copper wire, will be wound over this. Okay, and see these are the two ends of the wire. Suppose this is positive, this is negative, kind of that. Okay, so the current flowing through this uh, will be having different directions through this wire. If this is negative, then current direction will be this. If this is positive, current direction will be like in this way. Okay, so this will be saying, I think the previous. Okay, so look here. So this kind of solenoid, when it is the wire is actually wounded over a hollow, a PVC pipe or something like that, insulating material, then this kind of solenoid is called air core. Air core. Core means what? This part, interior part of the solenoid is called the core. But if there is no material, then only what you have? Air. So that's why this is called air core solenoid. Air core solenoid. So if you want to magnify your strength of the magnetic field, sometimes you can insert a material through this, okay, of the same radius of the solenoid. So here look this. So generally soft iron is being inserted in the core of this solenoid. So that's why uh, this is called soft iron core. Soft iron core. This type of solenoids are called soft iron core solenoid. So in this case, we'll see why do we need this after calculating the magnetic field for a solenoid. Okay, so these are solenoids. So I hope you have got some idea about solenoid. Now what we'll do, we'll just calculate magnetic field for solenoids before that and applying Ampere circuital law. So yeah, before that, so this is actually, suppose this is the cross section. If I have a cylindrical part like the cylindrical solenoid, if you just cut it open and then take one part, okay, take one part. This is the cross sectional view of that solenoid, okay, cross sectional view, and see the windings of wire. Okay, so you have to actually use any. Uh, so this is the wire. This is starting of the wire. You have to use it power source or a current source. Okay, suppose the battery is connected, some DC battery or AC battery, AC also you can, AC power supply also you can use. So current will be actually sent through this wire, and that will create magnetic field along the axis of the solenoid. But how do you say along the axis only magnetic field is created? What about the magnetic field? Suppose this is solenoid, this is a cross-sectional view. So if it is a solenoid, so what is the magnetic field outside the solenoid? For infinite solenoid or long solenoid, the B is actually 0 outside the, okay? Both sides. This side also 0, this side. Only magnetic field will be remaining uh, in the direction of axis, okay? In the direction of axis. Interior space. So magnetic field will be there in the interior space alone. Okay? In the interior space. And the magnetic field will be, so this is called axial magnetic field. This is called axial magnetic field. What is this called? Axial magnetic field. Okay. So only 4 people are there. So shall I continue the derivation of the magnetic field due to this solenoid, or shall I do in the next class? What do you think?
Sir, do it. Sir, do it for the next class.
Okay, then
Do
we'll
it
do
for
it in the next class. Okay.
Yes, sir.
And then
Many
you
are
have,
absent.
yes. Okay. Okay. So and then I'll stop the class now. Yeah.
Yes, sir. You
Is it
can.
okay?
Okay, sir.
Okay. Okay then. Okay then I'll stop the class here. See you on the next day, Wednesday. Okay. We'll derive the expression for the magnetic field for this solenoid. And in fact, there are many other physics also along with this solenoid. So I don't want other people to be deprived of that knowledge. Okay. So that's why I'm stopping it here. Okay. Okay. Actually,
Okay,
the problem is, like the people are not joining in time. I started around 6:10, even later that, isn't it? But then I get effectively some 50 minutes. So how much I can cover? So people should be joining in time so that we can at least get full 1 hour to cover a well amount of like physics in 1 hour class. Okay, anyway, so guys, I'll meet you on Wednesday. That day we'll talk about both solenoid and this toroid application of the Ampere circuital law. Okay, okay, then see you. Bye for today.